All right, we are now in part 3 of discussing ways to strengthen a metal. A quick bit of review. The first way we discussed was alloying. By simply putting an atom of a different size into a metal, you will strengthen it, and that was covered in part 1. That's kind of a zero-dimensional way, right? So because an atom on a lattice kind of is sitting at a point. The second way we discussed was through cold working or strain hardening, there's a few words here. Cold working. This is deliberate introduction of dislocations in order to strengthen the material. So dislocations are kind of, remember how they end on a line? It's kind of a one-dimensional way of strengthening a material. This third way is by reducing the grain size. Okay, and remember, a grain is a region of single crystallinity. And by making the grain size smaller, right, we can strengthen a material. And so why? Why does reducing the grain size increase the strength of a material? Well, if we sort of just draw a cartoon of a micrograph, and we've got grain 1 here, and grain 2 here, and grain 3 here, each of these is a region of single crystallinity. So the planes are all lined up in a specific direction, and they're in a different direction here, and right, all the lattices are lined up, and they're in a different direction here. Right, and so if I'm a dislocation and I'm in a part that is being subjected to a load, a tensile load, so I'm a dislocation, I'm moving along, I'm in a closed packed plane, I'm happily slipping this way. All right, now I hit a basic wall, right? Because my slip system, my closed packed plane along which I'm moving, isn't lined up in this crystal. I will have to overcome an energy barrier associated with this grain boundary, and I will then need to adopt the direction that is favorable for my slip as I move into that grain. And then when I encounter another grain, right, I might have to change direction again. And again, and again. So every single grain boundary that a dislocation might encounter will either stop it, like period, or it will slow it down immensely. And so the smaller the grain size you get, the more strength you're going to get. All right, and so now let's solve this problem. This problem is asking us to calculate these constants in this equation, which is called the Hall-Petch equation. So it's asking us to calculate that value stress sub naught, and then this value K sub y. They're constants for this particular alloy. And so we have the data given here, and I've pulled off some numbers carefully, and I've pulled off that at this value of 204.2 megapascals, the grain size, or actually 1 over the square root of the grain size, is equal to this value of 13.9. And then secondly, I've done it for another point. So I've pulled off those 2 points just to save a little bit of time. And now what I'm going to do is write the equation out with these two unknowns. So 204.2, this is megapascals, is therefore equal to the thing I'm trying to find, sigma sub naught, plus ky, a second thing I'm working to find, times d to the minus 1/2. But in this case, I know that d to the minus 1/2 is equal to 13.9 millimeters to the minus 2. And then the second equation I can write, so that I'm going to call that equation 1. The second equation, I'm just using, that was the data from 1, and now I'm going to use the data from 2. So I'm going to write that 65.3 equals sigma 0 plus ky times 3.1 millimeters to the minus 2. And now I'm going to subtract. And when I do that, 204.2 minus 65.3 is equal to 138.9. And that will equal, notice that these subtract right out. I will have a ky times this difference of 13.9 minus 3.1. Let's just write that down, 13.9 minus 3.1, which is 10.8. And so ky will equal 138.9 over 10.8, which is 12.86. All right, now what I want to do is take that number of this ky that I just found, and I'm going to plug it into my equation, either 1 or 2. It doesn't matter too much which one you do. Let's plug it into this one. When we do that, we will get that 65.3 is equal to sigma naught plus 12.86 times 3.1. With the units. And that, if you solve for sigma sub naught, you will get that sigma sub naught is 25.43. And now that we know those two constants, right, we can figure out the yield strength at any point, and this problem asks us to figure it out at that point. So we can write that the yield stress, or the yield strength, is equal to 25.43, and these are still in megapascals, plus it was 12.86, and now we will plug in our d to the minus 1/2, so that is d, so we will do 9.0 times 10 to the minus 3 millimeters, and we must raise it to the minus 1/2 power. You go ahead and do that, and what I get at the end of the day is 161 megapascals. All right, so the principle is solving two simultaneous equations, and you know, I just encourage you to, if you understand the principle of it, do not worry if you're not getting the exact answer that your homework methodology may be asking you for, because I couldn't do it either. There's just something funky about the data. So this is the principle. If you're applying the principle correctly, I believe you understand it. And even more than being able to solve this problem, what I really want you to know is these sort of basic principles, right? So you can slow down a dislocation by putting a different size atom in the lattice, right? That's alloying. You can slow down a dislocation by filling it up with dislocations, by cold working it or cold rolling it or doing something to it. And then the third thing you could do is you can reduce the grain size. And the reason why is always the same. These things slow dislocations. And remember, like, we've been looking at the yield strength, and what this is telling us is that on the stress strain curve, remember the yield strength is the point at which it deviates from linearity. So what this is telling us is that if you reduce that grain size, you're going to increase that yield strength a lot, right? And so you can get a much bigger yield strength by reducing the grain size. And of course, we already know from what we've learned that that'll come with a trade-off relative to its, ductility. In other words, it'll fail at a shorter length than it would if you didn't strengthen it. On the other hand, look how huge, an increase in yield strength we can get. And on this plot, you can see you can move from yield strengths of what, like 25 at large grain sizes all the way on up way past 200. So an order of magnitude increase in yield strength can be realized as a result of refining the grain size to be a smaller value in order to slow the dislocations. All right, let's close it up.